Okay, so welcome to the Internet of Water Peer-to-Peer Network webinar series. Today, we continue from last week with our in-depth two-part practical workshop on tools to work with geospatial hydrologic data via web services. So the first part of this series last week focused on R and introduced a lot of tools and processes to access data from online sources, both with and without web services, and how to bring that data into your workflow ready to use. So if you're interested in that and missed it, we have links on our website to the recording and the presentation materials. Today, we have the second part of the workshop, which focuses on Python. So my name is Lucas Stevens. I'm a policy associate at the Nicholas Institute at Duke University, and I'm your host for our workshop today. Today, we will cover a suite of free and open source geospatial water data manipulation tools in Python. Our presenter, Tahir Changini from the University of Houston, will walk you through the capabilities of these tools using specific examples as context and background. So feel free to follow along and use the packages for sample applications during and after the presentation. So you'll also have a chance to interact with the package authors. Along with Tahir, we also have Mike Johnson from Linker, who we heard from last week, and he'll be here to answer any questions that you have and help out. So I'll hand it over to Tahir to get us going in just a minute. I just want to go over a couple of housekeeping details, as always. So we are recording the presentation today, and just like we did last week, we'll post the presentation and the workshop materials as links on our website. So if you have to leave early, or if you want to share the presentation with friends and colleagues, then please do. It will be available for you later to do so. And then following the presentation, we're going to have some time to ask the presenters questions, and you can submit these in any time into the Q&A box. And for some of them, we'll try to answer them as they come up, since this is a more of a practical tutorial. If we get a whole lot of questions, we'll probably end up saving them for the end so that we can get through the material. Any administrative issues, for example, if the audio or the video isn't working, go ahead and put these in the chat box and we'll try to get those fixed as soon as possible. Okay, and with that, I will turn it over to Tahir to lead us through some hydrologic data manipulation in Python. All right.
Can you guys see my screen now?
Yeah, that looks good.
Great. Hello, everyone. My name is Tahir, and thanks for joining us today for the second part of our workshop. Last time, Mike went over some of the basics of geospatial analysis, and although some part of it was in R, some of the main concepts are similar, whether in Python or R. So I'm not going to repeat those, but there is a link in the web page, in the website that you see here that this presentation is. You can kind of check out the material from the last presentation that we went over some of the kind of basic concepts regarding the types of data that are available and web services. So today we are going to focus on Python and then try to introduce some of the equivalent packages that you can find, the things that Mike introduced last time, like SF, Terra, and MapView. So I will try today to introduce some of the packages that you can use to produce some of this stuff in R, that was done in R in Python. Let's just start by going over some of these geospatial packages that are available in Python. This is a non-exhaustive list, and I kind of posted a link here, Awesome Geospatial. There are kind of many more packages that you can go and try to figure out. But these are the things that we are going to use today, at least some of them. So I'll just go over some of these packages and introduce them, and then I will start the tutorial that we have prepared for this workshop. The first package is called PyNHD. And so it's part of the High River package that I developed. There are 7 packages in High River, and 4 of them are listed here. PyNHT is for navigating and subsetting NHT plus datasets, both medium resolution and high resolution. You can kind of navigate upstream and downstream, and then if you want only a part of the river network, or if you want to get some of the kind of outer network attributes, then you can use kind of PyNHT in order to kind of access those. We are going to show you how you can use PyNHT in order to kind of reach the purpose that's the research question that we have in this tutorial. And then Py3dep is for accessing topographic data. It uses the 3dep program, 3D elevation program, which is from the national USGS's kind of the national map service. And you can kind of access all sorts of data at any resolution. And PyGeoHydro provides access to many data sets like NWIS, National Inventory of Dams, and water quality, NLCD, HCDN, and also even CAMELS, or the actual evapotranspiration. So there are many data sets included in PyGeoHydro, and PyDayMet is only for accessing the climate data and working with climate data, both for single points, for single coordinates, or for gridded data. And this uses the Daymet database. And so these are the packages that for accessing web services. And excuse me. And the other packages are essentially the ones that are used within the High River, and also you can use later on for kind of manipulating the data that we retrieve from our packages. So X-ray and Rio X-ray are working for kind of gridded data. Rio X-ray is an extension to X-ray and is for working with raster data. It's somewhat similar to Terra in R, but for X-ray and Rio X-ray are the ones that we are going to kind of use in order to manipulate, clip the data, reproject our data sets that we have. And then GeoPandas is working for vector data, and ProPlot is for kind of doing most of the kind of plotting. It's a light wrapper around Matplotlib. This is the one that I usually use in a set of Matplotlib. I use ProPlot for all of my research, and even kind of it's for doing kind of production ready plots. It's a very great package. And the next one is Folium. And this Folium is kind of similar to MapView in R. It's for kind of making some visualize the data using Leaflet, which is kind of based on with vector and raster data, and you can do some interactive maps with Folium. So these are the packages that we are going to use. And as I've said, there are many other packages. You can go to this link, and then you can find some other packages as well. And for this presentation today, we are going to focus on impact of dam on a stream flow. So we are going to use the tools, specifically PyNHT and PyDaymet, in order to do some analysis on the impact of dam on kind of the stream flow. So I provided two scientific papers, peer-reviewed papers that you can go and then have some kind of idea about the background and the kind of methods that are available for doing this kind of analysis. But today we're going to keep it really simple. We're not going to go over kind of really complex ways of studying the impact of dam on the stream flow, and we're just going to only rely on visual inspection in our analysis. And also we are going to limit our study into Texas. We are going to take a look at whole Texas and then look at the dams and the streams that are available in Texas. And also for the time period, we are going to look at from 95 to 2005. The general overflow that we are going to go over today are, first, we are going to kind of take a look at all the gauge stations, all the USGS stations that have stream flow data available within the period of our study. And then we are going to kind of get all the dams in Texas that have been built around or kind of in the period of 95 to 05. And after getting those data, then we are going to filter out the stations that are not that don't have any dams within the 10 kilometers of upstream or in their upstream. And once we kind of filtered all the stations and all the dams that are upstream of those stations, then we are going to kind of analyze the upstream flow and then see before and what are the impact of building dam before and after the dams were built. So as I've said, we are going to only do a visual inspection and check what are the impacts, but there are some advanced ways of kind of quantifying the impact of dam that we're not going to go through today. And the last thing that we are going to do is that we're going to look at the land use, land cover data and see if we can find some correlation between the land use and then the dams that were built. So as I've said, the first step is to get stream flow data. We are going to use the NVIS web service, a National Water Information System. They have kind of all the data for stream flow data as well as the information about the kind of gauges. So we're going to first load some of the packages. We're going to use GeoPandas, and more importantly, we're going to use PyGeoHydro for accessing NVIS data, and PyNHD for accessing kind of the river segments from NHD plus data set. So as I've said, we are going to set our starting date from 85 to 2015. And the reason that, as I've said here, we are going to look at 95 to 05, but in order to add some padding years before and after building the dam, we've added 5 years because building dam takes some time. So therefore, we added 10 years more in order to kind of have more data to work with. So the first step is that we want to get Texas. We want to get the outline of Texas state. And next, we are going to take a look at all the stations that are available in Texas. And the way that we do it is that we're going to use the NVIS kind of class from PyGeoHydro, which kind of connects to the NVIS web service. And then we are going to query the data that we need. So the way that we do it is that, say, we're going to get all the data only for Texas. So we are going to use these kind of keywords in order to kind of identify our query or build our query. So we are going to limit the search only to Texas and a start date and end date based on what we specified before. And then what we need to also specify is that we want to make sure that the stations that we are querying have only daily, should include daily values, because some of these stations, they have instantaneous values, hourly or kind of minutes, but we are interested in those stations that have kind of daily value. So we want the output and the data type that are available should be daily. And the last thing that we want to specify is the kind of the parameter code, which as Mike mentioned last week, the parameter code of 0060 is for discharge. So you can use PyGeoHydro also provides you a data frame of all the kind of parameter codes. You can kind of query the parameter codes to figure out, what are the parameter codes associated with discharge. So you can also kind of use that functionality of PyGeoHydro, but we know that this is the one that we are going to use. So we are going to pass on this query to the NVIS function that we have. NVIS has a function called getInfo, and this function is only for getting the information about the USGS sites. So these are not the daily discharge data yet. So once we print a query, we see that there are around 4,000 stations within Texas. We are going to use ProPlot in order to plot the stations that are available in Texas. So now what we want to do next is that we want to figure out of these stations, which one of them have kind of enough data or daily discharge. So as I've mentioned, the daily discharge means that we need mean data, like mean daily discharge. These are not instantaneous data, right? So we are going to filter out all the sites that we retrieve from here. We kind of use sites for that. So then we are going to say that only keep the stations with parameter code of 0060, and the stat code should be 003. And this kind of indicates that this is a mean discharge. So there are different stat codes, as I've mentioned. You can use PyGeoHydro to figure out what are the available parameter code stat codes. So this one is going to say that mean, and this one is going to say that it's daily discharge. So mean daily discharge. And next we want to say that the stations that should have at least 30 years of data. And the variable for that is called count new. And then the next one is that we want to only select those stations that are not pristine. And then for that, we are going to use HCDN data. So once you get the data using this getInfo function, it automatically kind of retrieve the data related to HCDN from different sources, and then it's going to return it whenever you request using this getInfo function. Just be aware that HCDN by default is not retrieved from NVIS dataset. But regardless, we are going to kind of only keep the stations that are not pristine, meaning that they have been impacted by human activities. And lastly, we are going to only keep the stations that have in the drainage area of more than 10 square kilometers. So these two, the drainage square kilometer and HCDN 2009 are not included in NVIS dataset. Rather, the getInfo is going to retrieve it from other sources. So we can see here that we are from 4,000, we are down to 280 stations that match our criteria. And then we are going to just plot them. You can see here that these were the stations that we had previously, and these are the stations that match our criteria from a stream flow point of view. Next, we are going to retrieve the dams. So PyGeoHydro uses the National Inventory of Dams. National Inventory of Dams has a kind of RESTful web service that you can query data. These are kind of the most updated data from the National Inventory of Dams that is hosted and maintained by USAC, by U.S. Army Corps of Engineering. So the first thing that we want to first connect to the web service NID. We can do so by instantiating the class, the NID class. The first thing that we want to do is that, because we have two criteria. First, we want to get the data for Texas, and then we want to kind of make sure that only get the dams that have been built from 95 to 05, right? So first, we want to get what are the available fields that we can query. The way that we do it is that whenever you instantiate NID, it's going to kind of get all the valid fields that the NID web service accepts. So here we are going to say that take a look at all the valid fields and only find the fields that include year. So we can see here that there are 3 fields from the from NID web service that include year. So year completed ID, and years modified. So we know that we should use the year completed. The next one is that we want to find the state. So if we search for a state, we can see here that these are the kind of available keys. And what we want to do is to use a state key. If you want to use a state, then you need to provide Texas. But with state key, you can kind of can use TX. So once we know that these are 2 keys that we want to use, then we start making the actual query from the web service, from the NID web service. So we can use the function called get by filter. There are different methods. You can go through the documentation for other methods that are available for NID, but we are going to use get by filter, which is the most common whenever you want to kind of query from NID. So we are going to say that only get the dams that are within Texas, and the year completed should be between 95 and 205. So this is the format that you need to provide whenever you want to provide minimum and maximum bound for some variable. So we want to say that with these two criteria, get all the dams, and then we're just going to plot the dams and also the stations. So the first thing that we notice here is that we can see here that there are some dams that don't have any station, USGS station that match our criteria within their vicinity, and there are some stations that don't have any dams. So the next step is that we want to filter out all those dams or the stations that don't have any dam or a station within 10 kilometers of them. So the first step is that we are not going to, for now, care if they are in upstream or downstream. So we are going to kind of only look at the stations, only look at dams and stations that are within a radius of 10 kilometers. Next step, we are going to kind of worry about how we can filter it further down to only include those in the upstream. So what we want to do is that we want to kind of first we want to take a look at the drainage area of these stations. So we are going to plot a histogram of the stations, and we can see that most of the stations have a drainage area of less than kind of 15K square kilometers. And the way that we are going to kind of use this information is that first we are going to define a function in order to filter the based on the distance. We're going to filter the stations and dams only based on distance. So we are going to use a function from GeoPandas that I would highly encourage to try to kind of use. That is called query buck. There's a special index kind of accessor whenever you use GeoPandas. You can, for whatever data set you have in GeoPandas, you can use the accessor of a special index and then query based on distance. This one is kind of a highly efficient way of querying based on distance. If you use kind of the usual functions that are available with GeoPandas, they are going to be slow, especially when you use large data sets. So we are going to use query buck. So essentially this query kind of buck method is going to kind of use some of the special index methodology to make it as efficient as possible. So what this function does is that first it's going to kind of reproject the input data set into 5070, into EPSG 5070, which is essentially is going to make our distance, convert the distance into meters. And the reason that we want to convert it into meters is that this query is based on distance, right? So what we want to do is that we want to convert it from whatever we get into meters and then multiply it and then buffer around that area based on some distance. So as I've mentioned, what we want to do is that we want to buffer around, for example, each one of the stations a 10-kilometer radius and then search if there are any dams within that 10-kilometer radius. So this is what this function does. It's going to query all those dams and a station, and it's going to only keep those stations that are within, that have some dams within their 10-kilometer vicinity or this distance. So our first criteria was that we want to filter based on 10 kilometers. So we are going to pass our sites and dams to the function that we just wrote here. And then we can see here that after kind of applying this function to these two data sets, then we are going to kind of take a look at the drainage area. That then we can see here that this is the new distribution. This is what it was before. And then after filtering those stations, these are the new data sets. These are the new sites and dams that are available. So once we plot them, you can see here that we went from this figure with 280 stations and how many, I think I don't have the number here. And we can see here that at the end, these are all the stations and dams that match our criteria, both from the stream flow point of view. We have enough stream flow data, and also they have some dams in their upstream or downstream within their 10-kilometer radius. So as I've said, this one is only for 10-kilometer radius. Now we want to further filter it down to only keep those stations that have dams in their upstream. We don't care about the dams that are in the downstream. So the way that we kind of achieve that is that we're going to use hydrolinking kind of data sets or web services. The one that we are going to use today is called NLDI. This network link data index web service. It's developed by USGS and includes and has all the information that we need for our purpose that we want to kind of navigate. We have one station, for example, this one, then we are going to navigate upstream of this station and then go, for example, 10 kilometer and then check if there's any dam on the kind of the flow line or the river upstream of that location. So we are going to use NLDI. First, we instantiate the class. This what the NLDI is in the PyNHD dataset, in the PyNHD package. So once we have that, we are going to iterate over all the gauge stations. So the way that we kind of achieve that, we are going to use NLDI function called navigate by ID. So we are going to navigate based on ID, and the ID that we are going to use is an MVIS data, is an MVIS kind of ID. So first we want to say that the source for this ID is MVIS, and then what is the ID itself? It's the agency code that we get from the size dataset. Agency in this case is USGS, and then we are going to kind of attach it the site ID. So we are going to iterate over all the stations that are available here, and then get the kind of the flow lines. We want to get the flow lines, and we want to also specify that go only 10 kilometers. So the distance that we see here is essentially distance in a kilometer. One thing that we need to be aware of whenever you want to use this navigate by ID function is that not all the USGS stations or all the IDs have some associated flow line. So this function, whenever it cannot find the kind of the flow lines, or it cannot find any flow line for the input ID, it's going to return those IDs. So that's why I have this kind of try except block here that is going to try, and then if it cannot find any, which in this case is an exception, it returns it throws an exception called zero matched. And whenever we have zero matched flow line, then we are going to append it as a no flow. So we don't have any no flow line available. We can see here that out of the 280 stations, 2 of them didn't have any flow lines in the NLDI kind of web service. So there could be some many reasons, not many, there are a few reasons that why those stations have not been indexed by the NLDI. But for now, what we are going to do is that we're just going to only ignore those stations. So what we do here is that we are going to kind of ignore those stations, and the way that we do it is going to filter out. We are going to kind of say that if there is a no flow, then don't drop all those sites, and then associated dams from the data frames that we just created. So we are going to use the same function that we've had previously, distance by filter, and then we are going to drop these 2 stations that did not have any flow line. Now that we have the flow lines, what we want to do is that we are going to find the flow lines, find the COM IDs. So if you're familiar with the NHD Plus dataset, NHD Plus dataset has a common identifier, which, or for short, is called COM-IDs. And then what we want to do is that we want to query all the flow lines that are associated with the dams. Because previously we only get the flow lines that are associated with the stations. Now what we want to do is that we want to get the flow lines that are associated with the dams. And then we want to kind of compare and see if the COM-IDs of the dams are within these COM-IDs or flow lines that are available in our NH2 plus data set. So essentially what this does is that we're going to use a function called COM-ID by location. This one uses the hydrolocation endpoint of an LDI service. So we are going to pass that. And again, NLDI functions, they have all of them have this kind of functionality that if there are some missing, they're going to return those missing IDs, whatever input data that are given to the function. So we are going to check if there are some missing data, then we just want to drop it. So you can see here that for all the dams, one of them didn't return any feature. Therefore, we are going to drop that. Again, there are a few reasons that might this happen, but for the sake of kind of simplicity, we're just going to drop whatever kind of dams that don't have data available. Now that we kind of get the associated COM-IDs for the stations as well as the dams, what we want to do is that we want to figure out, we want to attach the kind of USGS IDs, and then USGS IDs kind of the stations, and also the COM-IDs that we kind of got from these two functions. And the last step is that we want to kind of filter out those stations that are in the downstream, right? So we want to only keep those stations that have dams in their upstream. So we are going to filter out those stations that have dams in their downstream and not upstream. So this function takes care of that. It's going to look at the dams and the flow lines data sets, the data frames that we just created here, and then they are going to merge them and drop those that have NA in their dam ID. So we can see here that at the end we are going to left with 7 dams and 5 stations. We have 5 stations. For example, the first one, there are 2 dams for the first one. For the second one, also there are 2 dams. You can see here that some of them have 2 dams. So out of 7 dams that are available, they are associated with 5 USGS stations. Now that we filtered it down, the next step is that we want to take a look at the stream flow observations for these 5 dams. The next step is that, for example, we can kind of get the more information on the dams. If you need more information, you can use the inventory by ID. We already have the dam IDs here. You can just pass the dam IDs to the inventory by ID function of the NADI class, and you can get a lot more information about those dams. We are not going to necessarily use those, but it's a kind of a really good function that we can use. What we are interested in is that the only one that we are interested in is this year completed kind of functionality, because as I've mentioned, we want to kind of figure out when was exactly this year the building of dam was completed. And then we want to compare what was the stream flow before and after that year, kind of the year completion. So the next step is that we want to look at, based on this year completed, and then figure out for 15 years before and 15 years after. We can see here that if we kind of look at the data sets of the dams that we just generated previously, that we know we have dam ID and USGS ID, Now we want to make sure that we have the year completed dam is within the period of our kind of study. We can see here that for all these stations and for all these dams, the start and end dates, the year completed, start and end dates that data are available. These are kind of all the stations and dams that match our criteria. The next step is that we want to get the stream flow data. In order to do that, we're just going to use, again, the MVS kind of class that we instantiated previously and use the function called get stream flow. We're just going to pass the station IDs and then the start and end date for those stations. And then once you pass that, it's just going to kind of go over those two stations and retrieve the daily stream flow data for these stations. This a stream flow data, a stream flow function by default is going to return daily a stream flow data, but you can pass the IV or instantaneous also to get the instantaneous, but in this case we are only interested in daily, so we're just going to pass the IDs and start and end dates. Once we have that, we are going to kind of plot the stations, the stream flow ID, and the year that the dam was completed. So you can see here that for the first station, there's a noticeable difference before building the dam and after the dam. For the second one, we can see here that we don't see kind of anything from only the visual inspection point of view. And for the third one, as we mentioned, there are 2 dams that are available. Again, we don't see that much of a difference before and after. And for the fourth and the fifth one, we can see here that there are some missing data within the period. And the reason, because there are kind of noticeable, we can see here that from 92 to 2004, there are kind of significant amount of missing stream flow data. So we can see here that essentially the first one is a good stations from only visual inspection point of view to go and take a look at it further. So the last part that we are going to focus on would be that we are going to focus only on the first station that we saw a notable difference. Excuse me. And then see if we can deduce something from the land use land cover data. PyGeoHydro package also provides access to the NLCD data set. The way that we are going to, NLCD data set is a raster data set. And in order to query the data set, there are different ways that you can query. You can either query for points or for locations, for latitude and longitude, or you can query within a bounding box, or you can query within a geometry. So the way that we're going to do it here is that we're going to retrieve the upstream drainage area or catchments, local catchments for all those kind of flow lines that we retrieved previously. And then within those catchments or drainage area, we're going to retrieve the NLCD data set. In order to get the catchments, we are going to use, first, we are going to retrieve the upstream and downstream catchments, because in this case, we are going to kind of check what are the differences between the land use land cover in the upstream of those stations and of this station and the downstream. So what we are going to do is that we're going to take a look at 30 kilometers upstream of the station and then 30 kilometers downstream of that station, and then compare those land use land cover to see kind of what are the differences. We are going to use, again, the same function that we used previously, navigate by ID. We did the same thing for the MVIS. We are going to use the station IDs like we did previously. The only difference is that we are going to set the distance to 30 kilometers, but instead of having only upstream, we are going to also get the flow lines for the downstream. So If you want to get upstream, we want to get upstream tributaries, all the tributaries in the upstream, and then we're going to get downstream divergence. So we're going to get all these upstream IDs and then downstream com IDs. And then again, up to 30 kilometers. So we are going to merge these two or concat these two flow lines that we just retrieved. The next step is that we are going to get the catchments from water data dataset. So water data, again, it's another web service that is maintained by USGS, and it includes different types of data. The one that we're interested in is called catchment speed. Is the one layer that we're going to make the query. So we're going to instantiate the water data function and then get the catchments for the upstream and then downstream com IDs. So all the flow lines in the NHG Plus dataset, they have a corresponding catchment or which are called local catchments. Again, these are available in the NHG Plus. So what we are going to do is that we're going to get the catchments for all the IDs that we just retrieve, like all the flow lines. We're going to get their com IDs and then retrieve the catchments for these. And we can see here that we find these stations, we find these catchments, only the first 5 are viewed here. And the only additional thing that we're going to attach is that we are going to make a distinction which one of these catchments are in the upstream and which one of them are in the downstream. So we are going to just simply first say that create a new column and call it upstream, and then kind of change the values of all the catchments that their com ID are in the downstream com IDs. So we can see here that we added a new column and they are upstream and downstream to make this distinction. If we plot those, you can see here that they are plotted with 2 different colors. So the upstream catchments and then downstream catchments with 2 different colors. And we can see here that these are all the flow lines that we retrieve for the upstream and then downstream. This is our station, and then these are the dams that are available in the upstream. Lastly, once we have the geometries, what we want to do is that we want to retrieve the data, the NLCD data, or the land use land cover for the upstream and then for the downstream, and then compare these two. So the way that we do that is that we want to what we want to do is that we want to kind of get the NLCD data set, NLCD data for all the catchments first, and then we are going to filter it or clip it later on. So we are going to kind of get the union of all these geometry to create one outline geometry for the whole area. And then we pass it on to the NLCD by geo function. PyGeoHydro, this GH is PyGeoHydro. There are a couple of functions for NLCD, and the one that we are using is called NLCD by geom. So we are going to pass the geometry that we just created, which is the union of all the local catchments. And then we are going to get the data at 30-meter resolution. So the highest resolution available for the NLCD dataset is 30 meters, but you can request for any resolution. It doesn't make a difference. So in this case, we are going to kind of get the highest available resolution for the NLCD data. So once we have that, we can kind of take a look at the data. We can see here that the dimensions, these are the dimensions, and these are the data that we retrieve. So by default, if you don't specify what types of data you need, it's going to retrieve all the canopy, impervious, urban descriptor, and also land use land cover. Or if you want, you can only specify that you need cover data. You can specify it to the NLCD by geom and only retrieve the data for the cover data. The last thing that we want to do is that we want to, now that we have the data, we want to compare the upstream and downstream based on the land cover type. So first, we want to see what are the available land cover types. There are some helper functions in PyGeoHydro that kind of gives you all the legends and their definitions. For example, we can see here that 11 is open water, 20 are developed, and then we can see here that for all the other different types of land cover, what is the associated land cover type. The only thing that we need to be aware of here is that the background values are 127. So next, what we want to do is at first we want to plot all the data that we have retrieved. And PyGeoHydro has another helper function that gets the official colors for each one of these land cover types. So these are the official colors that are published by the NLCD dataset. And we just plotted. We can see here that, for example, all these land cover types, and then the kind of associated their associated description over here. Now, what we want to do for the last step is that we want to compare the upstream and downstream. PyGeoHydro has another function, helper function that we use here, excuse me, which is called cover statistics. And if you pass the cover data set, then it's going to automatically compute what are the percentage of all these different land cover types over the whole region. So we are going to pass upstream and then the downstream catchments. So here, the same example, we use the direction column that we created, and then we are going to filter and keep only those that are in the upstream, get a union of them, and then clip it using this function called xarray geomask. And then once you clip the land cover data set, we are going to kind of save them into two different data sets and compare those. We can see here that for different land cover types, these are the associated statistics. We are going to only use the percentage of essentially the coverage. For example, these are percentage values. Like this is 1%, and we can see here that in the upstream, 62% is herbaceous, while in the downstream, we have 50%. So we're going to compute what is the difference between the upstream and downstream for each one of these categories. We can see here that the most notable ones are these shrubland and herbaceous, that in the upstream, we have kind of 50% and 12% more shrubland and herbaceous. But when it comes to cultivated, in the downstream, we have 20% more cultivated land in the downstream. So visually, you can also confirm that, and we have some quantification here. We can see here that in the downstream, the cultivated land, which is the cultivated 80, right? So which is kind of the 82 is the cultivated crops. We can see here that in the downstream of the dam, cultivated lands cover more area when comparing to the upstream land. So these two methods that we just described, using only NLCD dataset and also the visual inspection based on only stream flow data, gave us some insight into the difference, the impact of dam when on the upstream of a gauge station. So you can see here that with just a couple of functions, we access data sets that usually, if you want to do all of these steps manually using different functions, it could be really time consuming. But with these simple functions, and then the web services gives us very powerful tools to get the required data that we need for our analysis. So all these, this notebook is available on the website. You can download the notebook. If you want, you can change the variables and rerun the notebook for the region of your study. And yeah, if you have any questions, feel free to ask now or reach out later on via email.
Thanks so much, Tyler. That was really great.
Sure.
And so, yeah, audience, feel free to go ahead and put your questions in the Q&A box. We've got a couple in here now. So for the land use land cover data, does the cropland data layer have an equivalent web source to the NLCD?
So cropland, yes, the layers with the NLCD function, if I understand the function correctly, the question correctly, the NLCD dataset has different layers, but the ones that are supported by these, where was the function? Right, the NLCD function, the ones that are supported are this canopy, impervious, descriptor, and cover. But the NLCD, the MRLC dataset has other layers as well. If you want, you can go to the, if you want, you can go to the NLCD, the MRLs, if I can go to MRLC, right. So if you go to MRLC, just wanted to kind of show you all the available layers of the science, the services product. These are all.
Just jumping road, the croplands data layer is a USDS or a USDA product. So it does have a web service, but it's not from MRLC or
right.
USDS.
Okay. Great. Yeah, thank you.
So that's a different agency.
Yeah.
And so does the Python package work with it as well, or is there a?
No.
Okay.
This one doesn't.
You do have generic WMS and WFS coverage services though in High River, right?
Yeah. Yeah, if you there are some low-level packages that are available with Hydro OGC. Hydro OGC. So this package called Hydro OGC gives you low-level access to some of these WFS and WMS and also RESTful. You need to have some knowledge of this type of services if you want to. It's kind of straightforward, but you need to have some basic knowledge. And there are some examples. For example, here for the WMS, if you know the URL and then you know the layer names, kind of there are some other things that you need to pass on. But if you want, you can kind of use this function in order to get that data with this. But yeah, these are the functions that you can use later on if you have some other data sets that are not included in PyGeoHydro. So the question is, okay. So about the question, if you want the YAML file, if you go to High River examples, there is this file called environment.yml, and these are all everything that you need in order to run that notebook. So yeah, if you just click on the link that you have, if you just click on this notebook that impact, you're going to be directed to the repository, and then in the repository you have this YAML file.
Okay, and so how long have these techniques and these sort of linked data sets been available to use like this?
I'm not quite sure when. I think NLDI has been around for 6 or 7 years. Mike, do you have a better estimation of that?
I think publicly it kind of came online about 1.5 years ago and has become more stable.
The NLDI itself.
Yeah, a lot of the data sets and things that you mentioned have been around for a while, and they've always been hosted through the ArcGIS RESTful services, but those are trickier to use. I think a lot of the federal agencies are moving towards these open standards, which allows awesome packages like all these ones that you built to not necessarily connect to them more easily, because there's a ton of work you've done to make these easy for users to use, but more in a more stable and a more consistent way.
Yeah, great. So people are still, I mean, Tahir, you're an example of people still figuring out how to use these things and how to be creative with them.
Right.
Can you tell us a little bit more about your own research and sort of how you incorporate these tools and these packages into what you're studying at Houston?
Right. So my main line of research is on urban hydrology, and for urban hydrology, we need to have access to many different types of data. And one of the main issues that I've had was that because I wanted to conduct my research over the US, and if I wanted to, I tried to do some of these data retrieval kind of processes manually, but I quickly ran into issues because it was really time consuming if I wanted to repeat the same process over some other region. So that's when I found out about these web services, you know, ArcGIS, the RESTful WFS and WMS, because many of these data, as Mike said, have been hosted on kind of the ArcGIS layers with different things. But accessing those data sets was really difficult because there wasn't any function that you can kind of quickly access them. And so I started building some functions for my own use. And slowly the functions that I created kind of became larger. So that's when I kind of decided to make it available for everyone. And when I saw the value and the ease of use that it brings for conducting, especially kind of hydrology research. So that's why I decided to make it publicly available and put it in a package that makes it easy for other people to use. But I developed it over, I think, 1.5, 2 years, if I'm not mistaken. All these packages, they were originally called Hydrodata. There was only one package, but as I developed and added more and more functionality, I divided the whole package into 7 packages, each one kind of serving different purpose, but they are a standalone.
Great. Well, thank you so much. And thanks again to you, Mike, as well. Again, I want to encourage our audience to go back and spend some time with the presentation materials and go back through the walkthroughs and practice using the tools, because these are definitely things that sort of profit from the time that you invest in them, and take some time to learn as well. Any final thoughts, Mike or Tahir?
Thanks for helping us hosting this workshop, and I hope that people benefit from these workshops.